And we're back. Welcome back from the weekend and happy Tuesday. Today we will continue on finishing up on our discussion concerning the VC dimension. But before we begin, some administrative bits. Homework number 1 will be due today, Tuesday, at 11:59 and 59 seconds p.m. So where we last left off, we talked about our proof that the VC dimension is equal to d plus 1. And we started out that proof by looking at the case where the VC dimension is at least d plus 1. We built a construction where we took a data set consisting of d plus 1 many points, and we selected what that data is to make it easy. And the following design matrix is square and therefore invertible. We then selected a target vector, which consists of all possible instantiations without restriction of d plus 1 target values. And so we enterprised to find a vector w, our hypothesis, such that sine xw is equal to y. The best way to do that is to set xw exactly equal to y. And because our design matrix X is invertible, well, we get W is X inverse times Y. Now, of course, that says that absolutely this hypothesis W can shatter a data set of size D plus 1. But we also noted the fact that our design matrix, it can be square, but it can also be rectangular. And as a rectangular matrix, it might not have an inverse, but it can have a left inverse. And if it has a left inverse, that means we can get a solution for this W. And this design matrix in that case will have more than D plus 1 of these vectors, more than D plus 1 rows. So it would have greater than D plus 1 rows and D plus 1 columns. And so this demonstrated that DVC, or VC dimension, is at least or greater than equal to d plus 1, where d is the dimensionality. So let's now look at this other case, and that's the topic for today. We're going to prove that the VC dimension, DVC, is at most d plus 1. Another way of saying this is that it cannot shatter any d plus 2 many points. So let's take a look at that cannot shatter any d plus 2 many points. So we're going to start out with a data set vector valued x1, x2, up to and including d plus 2. And so we still have more data points here than we have dimensions. And of course, if each one of these x's, including x0, is d plus 1 total dimensions, including the x0, the original d dimensions, and the additional dimension x0, which is set to 1, we have more data points than we have dimensions. And so a result from linear algebra says when you have more points than dimensions, then there must be some point, let's call that the jth point, xj, that is the linear combination of all the other points. Now let's assume that we have some of these weighted combinations for all I not equal to j. We have AR, that's our weight, times xi. And so some of these AIs are going to be positive, some are going to be negative, and some are going to be 0. So imagine then, since it's a linear combination of all the x's that give us xj, that some of these are going to be non-zero, some of these coefficients ai, whether they're positive or negative. And so let's define a dichotomy. And let's define this dichotomy in a specific way because we can define it any way we choose. We just have to show that we have all possible assignments of +1, -1 labels to our input data. There is no restriction on how you set the values of the data, the features. And so we're going to imagine now a dichotomy where each one of our vectors, or xi's, that has a non-zero ai. We don't care about those coefficients that contribute nothing to xj. We only care about those coefficients corresponding to some contribution to the definition of xj. And so we're going to imagine a dichotomy where each of the ai's, each of the x's, our points, with a non-zero coefficient ai, is going to have a specific label. And that label yi can be +1 or -1. It's going to be the sign of that coefficient AI. So if AI is positive, it's going to be a label +1. If AI is negative, the coefficient, it's going to be a label of -1. So that's how we're going to assign the labels, ground truth, and this is a type of dichotomy. Absolutely. And remember the restriction, we said any d+2 data points, a dichotomy. So here, now we're going to say xj, we're specifically going to assign it a label yj is -1. Now that's a dichotomy. Have an assignment of +1, -1 to all the xi's that contribute to the value of xj. And then xj we're going to fix to have a label yj that's -1. And now we say no perceptron is able to implement or shatter this particular dichotomy defined thusly. And so we're going to prove that is the case in order to show that no d+2 data points can be shattered by the perceptron. And so here, this is our definition of xj. Let's multiply both sides of equality by our weight vector W transpose. So we're going to compute the score. W transpose xj is just our W transpose times this expansion, that linear combination of AI xi that defines xj. And because W is a scalar, we can put that inside of the summation, and we get this expression, the sum, for all I not equal to j of AI W transpose xi. And so now, let's look at our definition. If we know that the label yi is sign of W transpose xi, well, we already said for this xj, the label is -1. But we also said inside the summation that the label associated with a particular xi is going to be the sign of its coefficient ai, right? The sign, whether it's positive or negative, is going to determine if it's a +1 or a -1. And so if this is the case, well, we know that, okay, well, if the label sign W transpose xi, if it's positive, well, we either get a positive AI and we have W transpose xi. Well, if W transpose xi is negative, so the sign of that is negative, we also have AI is negative because the label associated with this xi has to be the sign of AI. And so if AI is positive, sign of W transpose xi inside here has to be positive. Positive times positive is positive. Likewise, if the sign of W transpose xi is negative, that means our AI is negative. Negative times negative is going to be positive. So that means for each term for which AI is non-zero, we're going to have that AI times W transpose xi, each term within that summation has to be greater than 0 because this sign of our coefficient matches the sign of the score W transpose xi for each one of those components that contribute to the definition of xj. So what exactly does that mean? Well, if we have the sum of non-zero components and each non-zero component sum is positive, that means the sum of all things that are positive has to result in the left-hand side of equality also being positive. So if each one of these is positive, that sum of positive things also has to be positive. So what that means is W transpose xj must also be positive. And if W transpose xj must be positive, that means sign W transpose xj also has to be positive, or +1. Now that contradicts at the outset what we had assigned for the label -1 by the dichotomy that we defined. And so what this means is that the perceptron for this data set of size d+2 cannot shatter all possible of these dichotomies on a data set of size d+2 because it contradicts the original -1. It can't produce that dichotomy. where the sign of xj is -1. And so what does that mean? It means that we've demonstrated this other point, that the VC dimension, the number of the size of the data set that the hypothesis can shatter, is at most d+1. We've demonstrated that by showing it cannot shatter data sets, any data set, all data sets of size d+2. All right, so let's go forward. And this proves that the VC dimension is d+1. And d+1 in the perceptron is precisely the number of parameters. Now recall, when we augmented our perceptron in d dimensions, we added W0, where this W0 absorbed the threshold. And this W0 is one of our parameters. We have d parameters from the original linear hypothesis, and that added parameter, that W0, for a total of d+1. And so we had our W0 as a threshold. Let's look at what the interpretation is for our VC dimension. Now, if you go into a professional music studio, you see a control board, and this control board has several knobs and sliders, and they control the amount of acoustic energy is at certain sets of wavelengths or frequencies of sound. So you can get very precise slicing up of the sound for very precise control. And so the parameters create so-called degrees of freedom. Just like the stereo, you can control different aspects of the sound. With the parameters for your hypothesis, you can control different aspects of how the particular hypothesis set produces a dichotomy. And so they give you different ways of selecting a hypothesis. The number of parameters in something like hypothesis, and we talk about the real valued weight vectors, that's like talking about analog degrees of freedom. You turn one weight a little bit more and you turn down another weight, you get a different hypothesis, and it selects different hypotheses in a certain way. Now, when we go to the VC dimension, we abstracted in terms of dichotomies. And so the VC dimension, DVC, is an equivalent of a digital or binary set of degrees of freedom that expresses the selection of different hypotheses in terms of the dichotomies that these hypotheses can produce. And so we had some examples, and let's think about these examples. For the positive rays, we said the VC dimension, DVC, is equal to 1. Now here you notice we had a single parameter for the positive rays. We had anchor point that we called A. And so different settings of A defined a different hypothesis as expressed by the number of dichotomies it could produce. Then we went to the positive intervals. In that positive interval, we had two anchor points. And to give them a name, you could call the left anchor point, let's call that anchor point A. And the right anchor point, let's call that anchor point B. And so here we see the VC dimension, DVC, is equal to 2. And it's exactly the number of parameters. It's more expressive. And if you change these parameters, change the anchor points A and B, you're changing the dichotomy that this hypothesis is able to express. And so when we talk about these degrees of freedom, it's a little bit of a catch, because we don't count necessarily all of the parameters. We count what we call the effective degrees of freedom, because certain selections of degrees of freedom or changes might not give rise to a different dichotomy. Let's imagine the following perceptron, and we have our input, we have our sign, W transpose X, we have our output. And so for each one, we have our weight vector, W. Let's assume we had a single W, so it's a 1D perceptron. And then we also have our threshold, W0. So we have two parameters for the first perceptron. And imagine if we took the output of that first stage and put it into another stage, that's another two parameters. And then out into another stage, that's another two parameters. So that's a total number of parameters count of 8. And so here, each perceptron has a weight and a threshold, and the sequence from input on the left to the output Y on the right, that represents a single hypothesis that is indexed or defined by 8 parameters. But really, the second stage, third stage, and the fourth stage, each one of them contributes a count of 2 to the total count of parameters. Those parameters don't add much. They don't do anything. And so we really only have 2 effective degrees of freedom. And so when we talk about the VC dimension, what we're measuring is the effective number of parameters, those parameters that make a difference in the number of dichotomies that the particular hypothesis instantiation is able to produce or express. And so we can also look at the number of data points. And let's go back to the definition of the VC bound. And in that, we have 2 quantities that are affecting our probability. We said the probability of the difference, divergence, whether En tracks or diverges from Eout by more than our uncertainty or error tolerance epsilon, is at most bounded from above by the following bound. 4 times the growth function on data set 2n, and we had e to the minus 1/8 epsilon squared n. And so let's take this right-hand side of the inequality, and we're just going to call that delta. And so we have a dependence here on this delta, and we can recast this expression and think about how certain epsilon and deltas for each setting, how does n, the size of the data set, depend on the VC dimension. And so we want a particular choice of our epsilon and our delta, and we need to know how many examples do we need in order for learning to be feasible. And so if we look at this growth function, right, using that VC bound, we have a data set in n, and that is polynomial. We said if we have a polynomial growth function, then learning is feasible. And so that's polynomial in d, the size of the data set. And then we have this decaying exponential, all things equal, it depends on the size of the data set n. And so for the 2 interactions as expressed by this VC bound, we have the interaction between the size of the data set, we have the number of examples, and then we have our n. So in this plot, you want to have a small value for d, our dimensionality, and we're going to fix this value. We want it to be small, and we see how n, the data set size, changes with this d, this interaction. And so the polynomial then will dominate in the beginning, the polynomial in the data set size n, where d is the degree or the VC dimension. The polynomial is going to dominate, and then eventually the decaying exponential takes over, and it goes down to 0, or very small quantity, when learning is feasible, meaning that probability that En tracks with Eout is going to diverge very, very rarely. And so essentially what we're looking at is how many examples we need in order to get over this hump, this peak, if you will, where reasonable generalization performance begins to occur. And if we look at different settings for d equals 5, that's our blue line, d equals 10, d equals 15, our VC dimension, for different settings of d, we see the same behavior, only the number of examples we need, which is measured along the horizontal axis, gets bigger and bigger and bigger. And so we have a rule of thumb here that the number of examples that you need for learning to be feasible is roughly, rule of thumb, at least 10 times the VC dimension, dVC. So let's look at our generalization bound. Now we began with the VC inequality, and we had an expression which bounded the likelihood that En will diverge from Eout. And so we call this expression on the right-hand side of equality, let's call that delta. And so given delta, we can actually write an expression for epsilon by just doing some algebra. And so here we have our delta, right? We can divide both sides by delta. That gives us a 1 on the right-hand side for m, a growth function 2n over delta. And then we take the log of both sides. We can take this e, bring it to the other side, do a little bit of algebra, and we get an expression for epsilon. It's just this radical 8 upon n, ln, 4 times the growth function over delta. And let's call that omega. And omega, if we parameterize it by the free variables. Omega is a function of n, our data set size, h, our particular choice of hypothesis set, and delta, which is that probabilistic bound. And so we can invert this logic and essentially say that the probability, instead of saying that E in diverges from E out by more than some epsilon, we can invert this and we say this E in diverges from E out by at most this omega, which is parameterized by our data set size, our hypothesis set, and our bound on the probability, our VC bound. And so we can say that the probability that E in and E out is going to be less than equal to this omega, our epsilon, our definition for epsilon, is going to be at least 1 minus delta. Now, of course, if we invert the inequality here to less than equal to, we're going to change this to greater than equal to, and we have our 1 minus delta. Okay. So now we can say that with the probability of at least 1 minus delta, we have E out tracks with E in is less than or at most this omega, this complexity term, indexed by the data set size, the hypothesis set, and this delta, the VC bound. And so E in is typically, in practice, smaller than out of sample error. And so we have this probability, and we can rewrite E out minus E in, just drop the absolute value, is at most our complexity term, omega of n, h, and delta. And E in is what you minimize deliberately because we have control over that. And so if we take this expression and we add E in to both sides of the inequality, we get that E out is at most, it's bounded by E in plus this complexity term, this trade-off between our data set size, our VC bound, and the hypothesis set. And so in this, what it says is that this omega is the size of our hypothesis set, rather, is good for E in, but it's bad for the sum. You need to strike a balance between in-sample error and this complexity expressed by this interaction between the data set size, the hypothesis, and the VC bound. And so we can try to impact how we approximate out-of-sample error by controlling the complexity of our model. If we can control this omega, the complexity, that trade-off, we can actually get E in to be very close to E out. And we're going to examine how you control this complexity with a mechanism that we'll cover in a few modules that we call regularization. All right, so with that, I will end there, and we'll pick back up on Thursday. As usual, please stay healthy, please stay safe, and I'll see you all on Thursday.